All right, I misspoke. That was actually part 5. This is now part 6. We've got like 2 or 3 more proofs here that we're going to knock out. Um, and you're going to find some similarities in these proofs and the ones you just did. The difference, of course, being that you're going to have to write this proof out. Now, you're not going to freak out. You're going to plan it out well. You're going to review the pieces you don't know before you come back. In this particular case, you're looking right at the bat. We mentioned a parallelogram property. So I wonder if you're going to have to know that for the test, like that we asked it just 3 times, right? So let's just jump into it. Let's prove this thing. So first of all, let's highlight the triangles we actually do have to prove congruent. I have AED, which is actually this nice little guy on the left. And then, green. CEB, which is this nice little triangle guy hanging out on the right. Now we're told this is a parallelogram, so that means we can bring in a lot of different properties because parallelograms have a ton. But in the end, guys, we just want to prove this as congruent, so I'm going to do this the quickest and most efficient way possible. So since it's a parallelogram, there are a ton of properties that are true. Opposite angles are congruent. Opposite sides are congruent. Opposite sides are parallel. Diagonals bisect one another. So there's a ton of stuff we can draw. But again, I want to go with the fastest, easiest thing. So here's how I'm going to do it. I know, first of all, that opposite sides have to be congruent, and there they are. So I know that's one side because it's a parallelogram. The second thing I'm going to note is since the top and bottom are, since the opposite sides, are also parallel, I know I have some angle values have to be the same. So I know for a fact that this guy has to be congruent to this guy, and I'm going to name them 1 and 2 just to make it easier discussion because of alternate interior angles. Now, if you're having trouble seeing that, don't forget to draw on top of your diagram. Those are my parallel lines. That's my transversal. So 1 and 2 are definitely going to be congruent because they're in the alternate interior position. For that same, without changing parallel lines, I think I automatically get another set of angles using a different transversal. And I'm going to call this angle 2 and this angle 3. So I think what I built for myself is an angle side angle proof. I have the side AD locked in between angles 2 and 3 on the left, and I have the side BC locked into angles in between angles 1 and 2 on the right. So there's nothing left to do but actually write the proof. It's going to be an angle side angle proof. So let's write this saying, so angle side angle. So the first thing I'm going to write, and again we have to be careful here, I'm going to write AD is parallel to BC because it's given to us that it's a parallelogram, and so it suffices here. Because it's given to me, I know that angle 1 is congruent to angle 2, and that's going to be because of the alternate interior angle theorem. So that gives me one side. In fact, the same reason is going to be true for the other angle, so I'm going to rewrite it on the right. AD is parallel to BC because it's given, which tells us angle 3 is going to be congruent to angle 4, again because of the alternate interior angle theorem, albeit with a different transversal. And the side length is actually going to be smack dab in the middle. Why don't I change colors? We have AD congruent to BC. And again, I'm going to write this because it's given that it's a parallelogram, so it comes directly from that. So that's enough. I mean, since it's a property of a parallelogram, and maybe we should go back. We shouldn't be like it's given that. Let's not be lazy. ABCD is a parallelogram. Because it's given that ABCD is a parallelogram. I was saying those words, but you know what? Let's just go ahead and write it out. And one last time with feeling, it's given that ABCD is a parallelogram. Okay, so if I met the burden of ASA, I can draw on ASA to actually finish out my proof. So triangle AED is congruent to triangle CEB because of the angle side angle triangle congruence theorem. Bam, done. Next proof. So again, ABCD is a parallelogram. Awesome. Guess what? Again, very important. I want to prove that angle 1 is congruent to the sum of angle 2 plus 3. Okay. So to do that, let's go ahead and kind of jump into this. This in our planning step, we have to kind of realize a couple different things. One, that we have opposite angles that are congruent. So I'm going to introduce a new angle that's 4. Because ABCD is a parallelogram, angle 1 and angle 4 are congruent. Which then tells me that angle 5 is supplementary to angle 4. Then I also know that angles 2, 3, and 5 have to be supplementary as well. So I think this is enough. Now I know that you guys didn't necessarily follow what I just said, but let me map out what I mean. So I know that the measurement of angle 4 plus the measurement of angle 5 is equal to 180 degrees. I also know that the measure of angle 3 plus the measure of angle 2 plus the measure of angle 5 has to equal 180 degrees as well. So the first one is because they're linear pairs. The second one is because they're all in the same triangle, which actually makes some pretty interesting equations that I can combine. If they're equal to 180, they're equal to each other. So the measure of angle 4 plus the measure of angle 5 is equal to the measure of angle 3 plus the measure of angle 2 plus the measure of angle 5. So then, if I notice I have angle 5's on both sides, the measure of angle 4 is equal to the measurement of angle 3 plus the measurement of angle 2, which gets me pretty close to what I wanted. I want to show that 1 is the same as 2 plus 3, but if you notice that this is a parallelogram, 1 and 4 are actually congruent, which means that since they're congruent, they have equal measures, so angle 1, or measure of angle 1, is equal to the measure of angle 3 plus the measure of angle 2, which is exactly what I'm asked to prove. So that's not the formal proof, guys. It's important to note that that is simply just a very well thought out plan. A proof actually has to have justification, so let's go ahead and take this plan, rewrite it so it's actually extremely formal. And for this one, let's actually write it more in a 2-column style because I think it's going to lend itself a little better. So I think the first thing we have to establish that ABCD is a parallelogram, and I will say that's because it's actually given as a parallelogram. So immediately, if you're looking at my diagram, and that's a congruency sign gone bad, we have angle 1, which is congruent to angle 4, and that's because it's given as a parallelogram, or simply a property of a parallelogram. Okay, so now we can start kind of writing these in together, but before we do that, let's convert it to a measurement. Measure of angle 1 is equal to the measure of angle 4, and that's going to be the definition of congruency. So now we can start kind of in our relationships. So step 4 would be to mention that angle 4 and angle 5 are linear pairs, and therefore they are supplementary. I'm going to abbreviate. The reason being with the linear pair postulate. And if they're supplementary, that means the measure of angle 4 plus the measure of angle 5 would be equal to 180. And that's because the definition is supplementary. Alright, we're cooking with gas now. I can now bring in the fact that the measure of angle 3 plus the measure of angle 2 plus the measure of angle 5 equals 180 degrees. And that's because of the triangle sum theorem. And now I can start transitioning these pieces together. If 4 plus 5 is equal to 180, and so is that sum, I can definitely claim that the measurement of 4 plus the measurement of angle 5 is equal to the measurement of angle 3 plus measurement of angle 2 Oh, I'm going to cheat a little bit right here. Get out of here, line. Plus a measure of angle 5. And that's going to be because of this transition. So we're getting really close now. All we have to do is now subtract off the uncommon piece. So in step 8, I can definitely claim that the measure of angle 4 is equal to the measure of angle 3 plus the measure of angle 2. And that's just going to be because I'm solving. And last step, step 9, because I've established in this previous step, in step 3, that 1 and 4 are actually congruent, and therefore the measurements are equal, I can simply say that the measure of angle 1 is equal to the measure of angle 3 plus the measure of angle 2, and that's going to be substitution. Okay, and that actually finishes my proof. So careful planning can actually save you in the long run, and that's what you saw there. I simply just started realizing through the properties of parallelograms that I could flip 1 to 4. 4 and 5 get me into the triangle, and then since triangles and supplementaries have the same total, I knew I could algebraically manipulate what's going on. So keep in mind that what you're seeing here is actually just a plan, and then over here you actually have the formal proof. Alright guys, that is I think step 6, or uh, part number 6. I'm going to go and stop it here, and I'll do the last part in part 7.